Okay, so by definition, the set V1, V2 through Vp is said to be linearly dependent if there exists weights C1, C2 through Cp, where at least one C is not a zero, such that C1 V1 plus C2 V2 plus dot dot dots through Cp Vp equals zero. So here we have an example of a matrix, 3 by 3 matrix, and if we row reduce this matrix, first of all, we would set this equal to a 0, 0, 0 vector, and that's what we get here. And after we do the row reduction, we would find that the last row is all zeros. So therefore, x3 becomes a free variable, and you can express x1 and x2 in terms of x3. And since there is a free variable, this is consistent, and at the same time, there are infinitely many solutions depending on what x3 is. And if we just compute the values that we got here into the equation C1 V1 plus C2 V2 plus C3 V3, we would find that we would get a 0, 0 vector. So therefore, by the definition, these set of vectors, or this is, they're linearly dependent. And we're just going to show a case where, sorry about the light, it's getting a little funky, but we see another 3 by 3 matrix where if you actually set this equal to 0, 0, 0, you'd get a row reduce matrix where we have pivots in all rows, and therefore it has a trivial solution. So, and there are no free variables. So this matrix, the columns of the matrix would be linearly dependent, which is different from what we've shown previously, where the columns of the matrix are linearly, actually, this would be independent. My fault. Okay, so there's also other cases where vectors would be linearly dependent, and that's if a set of two vectors, or it could be more than two, where at least two vectors, at least one of the vector is a multiple of the other. So here we have an example of V1 and V2, where V2 is essentially 2 times V1. So since V2 is a multiple of V1, by definition, we know that these two vectors are linearly dependent. I mean, we could have another vector here where V3, and it would be 9, 3. Sorry. And this would still be linearly dependent. Then I'm just going to wrap up with another theorem where the columns of A are columns of A in a matrix, A referring to a matrix, are linearly dependent if and only if there's a non-trivial solution to AX equals 0. So this is just kind of summarizing I think the previous example, since this has a non-trivial solution with the free variable, we can know that the columns of A are linearly dependent. And I think that's about it for topics on linear dependence.